Hello, this is Dr. Grande. Welcome to my video on research designs in counseling. I want to start off by looking at some of the common terminology used in research. First, we'll look at groups, and there are two types of groups. You have control and experimental. So in a control group, that's a group that does not receive whatever treatment that you're studying in your design. So let's take a look at a research design that involves treating participants who have symptoms of depression. So the control group would not receive any treatment. The experimental group would receive the treatment. So say the treatment was cognitive behavioral therapy. The experimental group would be treated with CBT, and the control group would not be. The next term is random assignment. And what random assignment has to do with is how participants are assigned to the experimental group, or sometimes you may have more than one experimental group, and to the control group. Ideally, participants are assigned randomly. We call that random assignment. When they're not assigned randomly, we call it non-random assignment, or sometimes non-equivalent groups. There are particular instances where we don't have a choice. For example, we're given a data set that's already been gathered, where the scores have already been gathered, and we can't go back and rerun the experiment and randomly assign participants. So that would be a non-random assignment or non-equivalent groups. Another term is pretest. So this is an observation or a score taken from an instrument that occurs before the treatment. So you may use a depression inventory as a pretest, and you'll collect a score from that, and then you'll have the treatment, and then after the treatment has been administered, you will give that instrument again to the participants, and that's called a post-test, which is the last term I have listed here. So pre-test occurs before any treatment is given, and a post-test occurs after the treatment. It's very unusual to give more than one pre-test, but it's very common to give more than one post-test. And the most common situation where you'll see more than one post-test is when you're trying to measure how durable a particular treatment is. For example, in the depression scenario, you have a pre-test score of depressive symptoms, you have the treatment, and you might have a post-test at, immediately, right after the treatment, say within a few hours. Then you might have a post-test a week later, a month later, 6 months later, and a year later. So you can have several post-tests, but in most instances you'll only have one pre-test. Now moving on, taking a look at some of the notation used in research designs. Before I get started with notation, I want to clarify that the notation does vary from researcher to researcher. So not every institution, not every researcher uses the same notation. However, most of the time it does follow the convention that I have here. So in research design notation, R equals random assignment, N is when you have non-equivalent groups, C is when participants were assigned by cutoff, and this can mean a couple different things. Let's say, for example, that you have an experiment where you're in a city and you walk out into a city street, and the first 20 people that you run into that are willing to participate in your study are entered into the study, and after that there's no more, right? So you'd indicate with a C that assignment was by cutoff. Another example of when you'd use the notation, use the C notation, would be where you have a cutoff score in place in order for a participant to qualify for a particular study. So say that you had a particular research design and you needed participants that already had severe depression levels. Like you didn't want moderate, you didn't want mild, you needed severe. So you use an instrument like a depression inventory, and you only accept participants that fall into the severe range. That would also be assigned by cutoff. Then we have O, and that's observation. So for example, a score on a depression inventory would be an observation, and X, which is equal to treatment. Now I want to point out an important point about the use of subscripts. You can see I have a couple different examples below where I have the X there. You have X subscript A, B, and C, and then X subscript 1, 2, and 3. And this is an area where the notation really doesn't seem to have any type of standardization across institutions. Both are used usually interchangeably, and oftentimes they're used to represent different independent variables. Sometimes, however, it can become a little confusing because one or both of these methods can be used to express different levels of the same independent variable. So I'll give you an example. Let's say that we're looking at the effects of over-the-counter pain medication, and we're looking at Motrin, acetaminophen, and aspirin. Right? So X subscript A, B, and C. So A could represent Motrin, B could represent acetaminophen, and C could represent aspirin. Those are three separate independent variables. You may also see that same design with the X subscript 1, so X1, X2, and X3. Now the other way to look at the different notation, the different levels of treatment, would be to look at levels of the same independent variable. So let's say that we were talking about the acetaminophen treatment variable. So 3 different dosages of the acetaminophen. Say one dose would be X1, another dose would be X2, and then say the highest dose would be X3. Now because there's no standard for this, you really have to be careful in looking at the notation to see what XA, B, and C, and X1, 2, and 3 are really referring to. Are they referring to different independent variables or different levels of the same independent variable? And when a research design is explained, say in an outline format, for example, the meanings of the notations should also be explained. Meaning there should be no assumption that it's standardized, especially in terms of how treatments are notated. So moving on to some of the designs that you'll see, we'll start with non-experimental designs. Now my list of non-experimental designs and quasi-experimental designs is not comprehensive, it's not complete, but I have selected some of the designs that you'll see commonly in the research community. So a relatively common design in the non-experimental design family is the one-group post-test only design. It only has an experimental group and a post-test. So like all non-experimental designs, it's not practical to use for inferring causality. But again, sometimes because of logistics, it's the only thing that we can do. It's the only design we can use. So in a one-group post-test only, you have just one group, you administer a treatment, and then you take a measurement. In a one-group pre-test and post-test, it's similar except you have a pre-test. So it's a little more useful, but you still can't infer causality. So in a one-group pre-test and post-test, you have a pre-test, a treatment, and then you'll have a post-test. Now remember, the pre-test and the post-test are the same instrument. So if you use a particular depression inventory, for example, if we're studying depression, for your pre-test, you'll use the same inventory for your post-test. Taking a look at quasi-experimental designs, the example I have here is the two-group post-test only. This group has random assignment, an experimental group, a control group, and a post-test, but it does not have a pre-test, which means it's not what's called a true experiment. But it is considered quasi-experimental, which means you have some ability to infer causality. When you're working with quasi-experimental designs, you have some ability to infer causality, but you can't have the same level of confidence that you would if you're running a true experiment, and we'll get to a true experiment in a little bit. So in this case, you can see we have random assignment, and one group gets the treatment, one group does not, and then a post-test is administered. Now here's another type of quasi-experimental design. This is called an interrupted time series. And this has an experimental group, and the example I used here, a control group, but it doesn't have to have a control group, a pre-test, and a post-test. In this case, actually several pre-tests and several post-tests. So let me give you an example of why you might use an interrupted time series, or you might see one in scholarly research. Say that we were studying accident rates of accidents that were caused by driving while under the influence. And each observation represents the number of accidents caused by driving under the influence of a particular year. So I have a couple, in this example, I have a couple observations, but that could easily be 10. You could have 10 pretests. You have 10 years of data for, let's say, a particular county. And this data represents the number of accidents that can be directly attributable to driving under the influence. And then we have, in the second row, another county, and we have the same type of data for each year, the number of accidents that could be attributed to driving under the influence. So in the first county, we interrupt this time series with what we would call a treatment, but let's say it's a concerted one-time effort to reduce driving under the influence. So for example, maybe it's a 3-week campaign where every night sobriety checkpoints are placed at many different locations. And the word gets out, and a lot of people are arrested for driving under the influence. And then it stops. And then you start measuring, or you continue measuring each year. And you want to see if that concerted effort had an impact on the accident rate. In the control group, you would not have that concerted effort to enforce the law, and you'd see what happens when it's not there. So you can compare the two. Now the reason these are non-equivalent is because these would be separate counties, and you can't, that's not random assignment. You didn't randomly assign residents to a county. They were already in the county. So this would be non-equivalent groups, interrupted time series. Now let's take a look at the Latin square design. Now what the Latin square design does, and I know it probably looks pretty complicated just looking at this example, but it tests for the order effects of multiple independent variables. So in this example, the X with the subscript A, B, and C represent different independent variables. So in the example I used before, Motrin, acetaminophen, and aspirin. Not different dosages of one medication, but 3 distinct medications. And since you have, in this example, you have the 3 different medications, in order to test for all the order effects, you have to have 6 different random assignments, 6 different groups, because there's 6 permutations of those 3 independent variables. And remember, a permutation is an ordered combination. So to be accurate when speaking about Latin square designs, they test multiple permutations, not combinations. So I'll go through a couple of these. So in the first one, you have a random assignment. Then you would have XA, let's say the Motrin, XB, the acetaminophen, and XC, which is the aspirin. In the second column, another group, randomly assigned, another group of participants, randomly assigned to this particular group. And these are all treatment groups, by the way. And this group, the acetaminophen comes first, then the Motrin, and then the aspirin, and then so on and so forth. So you can see with 3 independent variables, it expands to 6 different groups you would need. So this design is not practical for that many applications. Only when you have some reason to believe that the order of the treatments is important. So now let's take a look at a true experiment. So this has all the features that we talked about before. This has random assignment, it has an experimental and a control group, and a pre-test and post-test. And this gives you the most authority, when you're running a true experiment, the most authority to infer causality. There are still other factors that can come into play, but this gives you the highest level of confidence when you're trying to infer causality. You have the random assignment to 2 groups. You have the pretest for each group. One group gets the treatment, the other group does not, and then you have the post-test. So again, recognizing those other factors that could be causal, what you're looking for here is a difference in the post-test scores to see if the treatment made what's called a statistically significant difference. So then I want to show you one last design, which is called a Solomon 4-group design. Now if you look at the first 2 rows, you can see that it's identical to a true experimental design. And if you look at the last 2 rows, you can see that's equivalent to a 2-group post-test only. So a Solomon 4-group design combines a true experimental design with a 2-group post-test only. And the reason this is done is to test for the effects of a pretest. Sometimes just by administering the pretest, there's an effect. And a Solomon 4-group design allows you to test for that effect. Now, you might be wondering why a Solomon 4-group design isn't always used, because it has the elements of the true experimental design, and it also tests for the effects of a pretest. And one of the major reasons that we would use a true experimental design and not a Solomon 4-group design that has the other part, the 2-group post-test only part to it, is because in the social sciences, often we really have to work diligently to gather participants. And there's a financial factor that needs to be considered, as well as other resources. So although this design seems ideal, you have to split the participants into 4 groups instead of 2, which could leave you with having too few participants in each group. So this design is somewhat common, but it does come at a cost. I hope this video on research designs and counseling was helpful. As always, if you have any questions or concerns, feel free to contact me and I'll be happy to assist you.